In this lecture, we're going to discuss nonlinear dynamic analysis using numerical methods. We're basically going to follow the same notation and formulas presented in sections 5.4 through 5.7 of Professor Chopra's book in Dynamics of Structures. There are basically two general classes of nonlinear behavior in structures. The first one is geometric nonlinearity, and this occurs when the small displacement assumption is not valid anymore. And the second type of nonlinear behavior occurs when the linear elastic material behavior, that is the linear relationship between stresses and strains, is not valid anymore. And then we say that in that case we have material nonlinearity. To consider some simple illustrative examples of geometric nonlinearity, on the left here, consider a pendulum of fixed length L subject to gravity. So you have a vertical force mg, and as the pendulum is swinging, if the angle theta, in this case is going to be our degree of freedom, if the angle theta is small, the restoring moment mgl sine of theta can be taken as mgl theta, because sine of theta and theta look very similar when theta is small. But as theta becomes large and the small displacement assumption is not valid, sine of theta is very different from theta. And so that becomes a nonlinear term in the equations. Another a little bit more complicated example would happen in the case here presented on the right, where you have a column subject to a lateral load P of t and a vertical constant gravitational force mg. As the column displaces laterally due to P of t, two things happen. Number one, there is a lateral displacement u that generates what is known generally as a P delta effect, which is the vertical load mg is now offset from the support, and it creates a moment. Now that moment will be very small if u is very small in comparison with h. But if mgu is comparable to p times its distance from the support, then that effect cannot be neglected. Moreover, when this cantilever begins to deform significantly, the height of P with respect to the support also becomes a function of the lateral displacement U. So you have a feedback effect where the displacement of the structure creates changes in loading, which in turn create changes in displacement. And so this is a more complex type of nonlinear behavior, and this is known as P delta effect, which can create instability in structures. In the material nonlinearity, as an example, you can consider a cantilever beam with a load at the tip. If that load is large enough such that the stress-strain relationship of the constitutive material begins to deviate significantly from the elastic range, which would in this case be shown like here. If the load creates stresses and strains that are beyond that, now we are in a situation where we have material nonlinearity. If you integrate those stresses in a given cross-section, you will integrate to a moment. That moment now will have a nonlinear effect because it's integrating stresses and strains that are nonlinear. And if you integrate that moment throughout the length, then you will end up with a nonlinear force displacement relationship as a byproduct. So this is a case where force and displacement will exhibit a nonlinear relationship due to not necessarily large displacements, but the constitutive material going beyond the linear elastic range. Moreover, if this load is cyclic and it's creating alternating displacements, it's possible that you have an ascending branch like this when the strains are increasing, and then a descending branch like this. And these ascending and descending branches do not have to be the same, and if they are not the same, as it happens in steel, concrete, and other materials, you will have permanent dissipated energy in the form of hysteretic loops, and that is an additional nonlinear effect that can create significant problems, but sometimes it can be turned into a useful effect, as it happens in base isolators and other types of damping inducing mechanisms.